In the last video we have classified the irreducible representations of SU3. So in this final part of the lecture I want to show you a nice application of these representations in particle physics. So SU3, perhaps after SU2, is the most important compact Lie group that appears in particle physics, and actually this is true for two different reasons. There are two ways in which SU3 appears, and they have to do with the quarks. So SU3 is prominent in, let's say, quark physics for the following reasons. So first of all, there is the color SU3 symmetry. So the color SU3 symmetry, this is the exact gauge symmetry in the standard model of particle physics. And what it does, well, this SU3 symmetry, it simply mixes the different color quantum numbers of the quarks. We know the quarks, they come in different flavors, so we have 6 different quarks: up, down, strange, charm, top and bottom. And each quark carries a color quantum number which tells us how it couples to the gluons in the standard model. So there are 3 colors. SU3 is a 3 by 3 matrix, so it simply acts on these states in the fundamental representation. But there is another place where SU3 appears, and this is flavor SU3. And it's not an exact symmetry, so it's an approximate symmetry that mixing the 3 lightest quarks. So, I mean, if we just look at the masses of the quarks, then there are 3 lightest ones, so the up, down, and strange, which have, okay, not exactly similar masses, because the strange is quite a bit heavier than the up and the down quark. But the charm, top, and bottom, they have much higher masses. So if we only look at the first 3 quarks, then one can imagine that there is some approximate symmetry that interchanges these, or mixes them. And in fact, it is an exact symmetry as far as the strong force is concerned. So meaning that the way that the gluons couple to these quarks, it really does not care about the flavor, so as far as the strong force is concerned. But the other quantum numbers and the mass, so the mass m and the quantum numbers which are, say, the isospin E3, isospin, and charge Q differ from one particle to the other. Okay, so there are these 2 symmetries. You may say that the color symmetry is more important in these days because it's an exact symmetry, and SU3, the flavor symmetry, is really only approximate. But still I want to focus on this flavor SU3 symmetry in this video. So this is the topic of this video, and the reason is that it played a very important role in the development of the standard model, and in particularly in the discovery of the quarks. Okay. So to understand why this is an important episode in the history of particle physics is the developments in the 40s, 50s, and 60s, where at particle accelerators, or collision experiment, one was observing a whole zoo of particles that had not been predicted before. And they had real trouble thinking of new names for all these different particles with different charges and different isospins that they were encountering. So in, say, 50s, there was a zoo of new particles that were showing, based on their charges and their masses and their isospin quantum numbers, some weird organization. Zoo of new particles showing weird organization in the sense that there were groups of similar mass particles. So for instance, these groups here with different values for the isospin and the charge, I3 and Q values, that formed these weird figures when you plotted them here. So similar isospin and Q values, values in weird shapes. So in these plots, one of the axes is not the charge Q, but it's the strong hypercharge. So that is given by y is, or let's put it differently. So the charge is related to the hypercharge by the linear combination of the isospin and the hypercharge. Okay, so they observed these symmetrical figures, and a real understanding was lacking at the time. But then came Gell-Mann, and also simultaneously some other physicists. They made this observation that perhaps we can understand these symmetrical figures by posing that these are not fundamental particles, but actually particles that are composed of more fundamental particles that are the quarks. So Gell-Mann said, perhaps these are composites of more fundamental particles that he named quarks. And in particular, he proposed that there would be 3 of them, which now we know to be the 3 lightest ones. Okay, so how does this work to start from quarks and then understand what these structures are using the irreducible representations that we introduced in the last video? So for this, how should we understand these quarks under the flavor SU3 symmetry? Well, we have 3 quarks, so they should be mixed just by the fundamental representation of SU3. So we have the fundamental representation of SU3, and this is often denoted just by its dimension, so boldface 3. So what should it correspond to? Well, it should correspond to these 3×3 matrices just acting on this basis. So if we write 1, 0, 0 to be the state corresponding to the up quark, 0, 1, 0, the state corresponding to the down quark, and 0, 0, 1 corresponding to the strange quark, then what would the action be of SU3 on a general state? So if I have a special unitary 3×3 matrix, it's just gonna multiply this vector in the obvious way. So this is a representation of SU3, so it should fit into the list of irreducible representations that we have found in the previous video. So let's see where exactly it is. And this is analogous to the question in SU2, where we noticed that the fundamental representation of SU2, it had to be two-dimensional, so it could only correspond to the spin 1/2 representation of SU2. Now here we can do a similar exercise, and in fact we can really just read off what the weights of this representation are, and then draw the corresponding diagram of weights. Right, so recall that the Cartan generators are given by half the third Gell-Mann matrix. So this is the matrix of this form. And the second Cartan generator was given by half the 8th Gell-Mann matrix, and it's given by this, so 1 minus 2. So the weights in this representation should just correspond to the eigenvalues, or the joint eigenvalues of these two matrices. And since they're both already in diagonal form, I can read off the weights just on the diagonal. Right, so let's plot them. In my two-dimensional weight diagram. So here I have my H1 and H2 generators. So the first weight is going to have horizontal coordinate 1/2 and vertical coordinate 1/2 square root of 3. So that one sits somewhere here. Then we have minus 1/2, the same height, so that's here. And then 0 minus 1 square root of 3. So that would be here. And by our definition of this basis, this corresponds to the up quark, the down quark, and the strange quark. Now the roots, where are the roots here? So the roots, they correspond to vectors like this. So we call this is alpha hat 1, alpha hat 2, simple roots. So now we can clearly see what this irreducible representation is. This is the highest weight, and to get the label of the representation we had to take the inner product of this highest weight with the two simple roots. So the inner product of this with alpha 1, so it's half the length, and I had to take twice this inner product, so that corresponds to 1, while it's perpendicular to the second root, so the second label is 0. So we get PQ is 1, 0. So instead of calling this the 3 representation or the fundamental representation, I could distinguish it by saying that its label is 1, 0. Right, so this really corresponds to this polygon that we mentioned last time, being like the smallest possible triangle. Now if you think about what you know about the charges and isospins of these 3 quarks, we can actually figure out how these generators, H1 and H2, the Cartan generators, are related to the isospin and hypercharge. And in fact, what we see is that H1 is simply the isospin, and H2 is the hypercharge up to the square root of 3. So let me be precise about. So this should be 2 over square root of 3 times the hypercharge. So maybe I should have shown you here where the lines of constant charge are in these diagrams. So okay, you can already see it from the labels or the names of these particles, since they all carry a label that indicates their charge. Since this is a linear combination, the particles of equal charge have to lie on lines. So they correspond to these particular lines. Where the charge corresponds to -1 here, 0, and 1 there. So the same is true for these other figures that I've drawn, if I've drawn them. Okay, so -1, 0, 1. Similarly here. -1, 0, 1, 2. So the way that we've plotted this weight diagram in terms of the Cartan generators, it is really of this form, right? Because up to a rescaling of the horizontal axis, this is just the hypercharge. So these quarks really correspond again to particular values of the charge, where this is -1/3 and this is 2/3. And for Q. Now, of course, the exercise is going to be is that we're going to compose these quarks into tensor representations, and that should exactly explain what is going on here. But we know when we compose quarks or build larger particles, there are not just the quarks, but there are also the anti-quarks that we can use. So where are the anti-quarks? Well, they live in the antifundamental representation. Antifundamental representation. So this is often denoted by 3 bar. So these should contain the anti-quarks, and since they are antiparticles, they should have opposite quantum numbers. So opposite quantum numbers. So in particular, the isospin and hypercharge should be their negative. So it corresponds exactly to taking this picture and reflecting it in the origin. Now we know how we can go from an irreducible representation with a particular label to its reflection. Well, that just corresponds to interchanging P and Q. So this is really the 0, 1 representation. So it looks like this, where now we have the anti-strange, the anti-down, and the anti-up here. So indeed, if you check their values of the charge, they agree exactly to the opposites of the ones that are drawn here. So what we can do now is we can take a quark, say, and an antiquark, and look at pairs of them. So we're going to ask how the tensor products of these representations decompose into irreducibles. So we're going to look at composite particles. So one option, these are the mesons, is to take a composite of a quark with an antiquark. So the way that they will transform under this flavor SU3 symmetry is in the tensor representation of the fundamental with the antifundamental. Because the quark transforms in this one and the antiquark transforms in that one. So this is a 9-dimensional representation, and there is really only one way that it can decompose, and that is as an 8-dimensional irreducible and a 1-dimensional irreducible. So the 1-dimensional, that's going to be the trivial representation. And what is this? 8. So this is the octet representation. But actually, we've already seen this representation because this is an 8-dimensional representation, which is the same as the dimension of SU3. So this is also the adjoint representation. Okay, and just looking at the general formula I gave for the dimensions of these representations, I can easily figure out that this should correspond to label 1, 1. And indeed, the weight diagram of this label 1, 1 irreducible representation, that is just a root diagram, right? Because the root diagram is the weight diagram of the adjoint representation. So that is exactly what we see here, right? It corresponds now to the polygon being the hexagon. And I said that there will be another state inside in this irreducible representation, and the multiplicity, when you go like inside an hexagonal ring, it increases. So here in fact I have a multiplicity 2 weight factor, and indeed 2 particles were known there with 0 charge and 0 isospin, corresponding to the neutral pion and this eta particle. So the explanation of this shape for these particles is that these are the mesons. So they're bound states of a quark and an antiquark. So how about these other two that are right there? So here also I have the same octet representation. But it does not arise from a bound state of a quark and an antiquark, but these correspond to the baryons, which are bound states of 3 quarks. So they correspond to a representation which is a tensor product of 3 times the fundamental representation, which decomposes as a 10-dimensional irreducible representation. Direct sum, 2 8-dimensional ones, and then trivial representation. So again, this adds up to 27, which is 3 times 3 times 3. So this is an octet again, and here we have the so-called decuplet representation. And actually this one does not occur in the Quark model for reasons that I won't explain further, but it has to do with the fact that all of these particles not only have internal quantum numbers, but they also have spin. So they transform also under Lorentz transformations. So in fact, what one should take into account here is that we do not just have a transformation under SU3, but under SU3 and the Lorentz transformations. And that will put some restrictions on how this can decompose. But we can already, from just looking at SU3, see that there will be a decuplet representation corresponding to now label 3, 0. And the octet representation, well, that's the same one as there. So it has PQ equal 1, 1. So recall from the octet representation there is a highest weight, which is this one, which has exactly, in terms of the roots, inner product 1 with that one and 1 with that one. And the decuplet representation, which is 10-dimensional, it has a highest weight, which is this one, for the delta plus plus particle. Okay. And okay, let me mention that these correspond to the spin 1/2 and these to the spin 3/2 baryons, which one could derive by looking at the Lorentz representations as well. Right, so these are the spin 1/2 baryons. So they again form this hexagon. And then we have the spin 3/2 baryons, which should form a 10-dimensional representation. So they should correspond to this highest weight, and then that should correspond to a triangle, right? And all the points that in the interior. But this was the nice realization of Gell-Mann, because there were not 10 particles known at that time. There were only 1, 2, 3, 4, 5, 6, 7, 8, 9. So there was a corner missing down here. So based on this SU3 representation theory, he predicted that there should be another particle. And not only that there should be some particle with similar mass to the other ones, he knew what its charge should be. It should have charge -1, and its isospin. So it should have isospin corresponding to this level. So we call this particle omega minus. And indeed, within 2 years, this particle is discovered. And this was really a very big evidence for the existence of quarks. And that's also what earned him the Nobel Prize in the 60s. Okay, so this is a nice application of the representations of SU3 that was very relevant in the development of particle physics.